Okay, so we're going to pick up where we left off here, and for this problem in particular, so you're definitely going to need a protractor and ruler for this. I'm going to do the best that I can to draw this on the screen freehand. You do your best with a protractor and ruler. Okay, so using the scale of 1 centimeter equals 8 newtons, determine the magnitude of each vector. Okay, so when I measured out the vector B, I measured this out to be 12 centimeters on my paper. And then so 12 centimeters, and using the scale that 1 centimeter represents 8 newtons, so 1 centimeter represents 8 newtons, that makes vector B equal to 96 newtons. And similar idea over here, I measured this out to be 6 centimeters, and using that same scaling factor, so 6 times 8, I get this to be 48 newtons. Alright, so it says construct a vector, it represents the resultant. So what I'm going to do is I'm going to draw in, there's two ways that I can go about doing this. I'll show you both. So I'm going to take one of the vectors, it doesn't matter which one I start with. Okay, I'm going to use vector B, and I'm going to copy that vector up here. So I'm preserving the direction, and so it goes to the right, and I'm preserving the magnitude, making the exact same distance. So I'm drawing an 12 centimeter line up here. Now my resultant goes from the tail of my first to the tip of my last. Okay, so my resultant would look something like so. Okay, so there's my resultant. Now another method of doing it is for two vectors that is called the Parallelogram Method. So I copied vector B, I already did that, and then I can copy vector A, and I can draw the copy of vector A over here. So this is my A copy, and this is my B copy, and my resultant goes from the two tails of my original vectors to the two tips of my two copies. Okay, once again, it's going up to the right, so that's going to be the important thing. So now I want to figure out the magnitude of my resultant. Okay, so I could do this in a couple different ways, but if I measure this out, I measure this out to be 13.5 centimeters. Okay, and then if I use my scaling factor of 13.5 centimeters, if I multiply this by 8, I get a value of 108 newtons. So my magnitude is 108 newtons. Now, of course, you could also do a squared plus b squared equals c squared. The direction, I got a direction of 26 degrees. If you measure the angle here, that's 26 degrees. So if point P represents a 15 kilogram object, what acceleration would the forces A plus B produce? Well, that of course acceleration and net force is Newton's second law. A equals F net over m, and my F net is the value of my resultant. So that is my 108 newtons divided by my 15 kilograms. And if you divide those two out, I got a value of 7.2 meters per second squared. What would the magnitude of the equilibrant force be? Well, an equilibrant, recall, is the same magnitude as my resultant, but the opposite direction. So it would be 108 newtons, and it would be in the opposite direction. Okay, so instead of 26 degrees above the horizon, it would be 26 degrees below the horizontal. Okay, so it's opposite direction. Okay. All right, next problem. We are looking at and I'm going to change the screen here. We're looking at a box is copper and the steel surface is steel. So if we look down below here, we want to show the scaling effect. So once again, we're using a protractor and ruler. So draw a force of gravity vector. Okay. So we have 100 Newton force, 100 Newton block, so 100 newtons, and I need to draw an arrow. I'm going to make this screen a little. There we are. I want to draw a 10 centimeter line that's extending from the center of the block. Okay, so you need to do this on your sheet of paper, but it's going to be 10 centimeters, which equals the 100 newtons. And that is my force of gravity. Okay, the next thing says calculate the mass. Okay, well, that is F of g equaling mg. So I have my force of gravity, so my mass then becomes my force of gravity over my acceleration due to gravity, so that's 100 newtons, divided by 9.81 meters per second squared. And if you go through and calculate that out, you get approximately 10 kilograms. Draw in a normal force vector. Well, the normal force and the force of gravity are the same exact value, but going in the opposite direction. So if the force of gravity is 100 newtons, then the normal force is also 100 newtons. So that would be a 10 centimeter line going up. It says calculate both the static force of friction and the kinetic force of friction. So what we need to use there is the Fun equation, and in order to get the kinetic frictional force, we need to have the kinetic coefficient, and for the static frictional force, we need to get the static coefficient. Okay, so if you look both of these up, the static one is 0.53, so this is 0.53 times 100 newtons, which of course is 53 newtons. And then the kinetic is 0.36 times the 100 newtons, which then of course is 36 newtons. And then it says determine the force needed to accelerate the block at 2 meters per second to the right. Okay, so in order to figure that out, I'm going to actually do that down here. So I'm going to do E down here. In order to do that, I need to first know what my F net is. So my F net is equal to MA, that's Newton second law again, and we have, it's a 10 kilogram block, so 10 kilograms, and we're trying to accelerate it at 2 meters per second squared. So the F net required is 20 newtons. So this does not mean my applied force has to be 20 newtons. It means my applied force has to be greater than 20 newtons greater than the frictional force. And if I want to keep this acceleration of 2 meters per second squared, then what I need is to have a applied force that is 20 newtons greater than the sliding force, that is the kinetic force of friction. Okay, so my applied force has to be equal to my frictional force plus my net force. It's got to be 20 newtons greater than my frictional force. So that's 36 newtons plus the 20 newtons, and so that of course is 56 newtons. So my applied force to the right is 56 newtons. So this should be 5.6 centimeters. Exactly. The end of this arrowhead should be 5.6 centimeters. And then my frictional force would then be the 36 newtons, so my force of friction, sorry if it's a little sloppy here, is 36 newtons, so that is, to the scale, that's 3.6 centimeters backwards. Okay, so the next one, just to kind of be clear on things, another scale of having a another one of having it, hang on, sorry, there we are. Another one of having it have a scale of 1 centimeter equals 4 newtons. Okay, so what we want to look at is we want to calculate and draw each of the following vectors. Okay, and this is just a slight different notation from Mr. Prusnowski and myself. I call this the weight parallel, and this I call the weight perpendicular, which is equal to the normal force. But either way, the mathematics of them are the same, just different way of calling it. So the first thing is find the force of gravity. Notice that we have a 2 kilogram block. So in order to find the force of gravity, this is the mass times the gravitational field. So this is 2 kilograms times the Earth's gravitational field of 9.81 meters per second squared. So this is 19.6 newtons. And so if we use the scaling factor that 1 centimeter equals 4 newtons, okay, so if I want 4 newtons is 1 centimeter, notice I'm putting it down below, so I want to cancel out the newtons. This is going to be 4.9 centimeters. So I'm going to calculate all these, and then we'll go back up and draw them in. My weight parallel is mg sine theta. So what I need to figure out here is the angle. Well, that's where the protractor comes in. I measured the angle to be 26 degrees. Okay, so this is 2 times 9.81 times the sine of 26 degrees. And when I went through and calculated that out, I got 8.6 newtons, which then if you do the conversion factor, 4 newtons is 1 centimeter. That works out to be 2.15. I'm just going to call it 2.2 centimeters. Okay. My weight perpendicular, this is my weight perpendicular, which is equal to my normal force, is equal to mg cosine theta. So this is 2 times 9.81 times cosine of 26 degrees. I worked this out to be 17.6 newtons, which then scaled 4 centimeters, and 4 newtons is 1 centimeter. That's newtons. This works out to be 4.4 centimeters. Okay, so now I need to draw a 4.9 centimeter block arrow down, okay, straight down, and then I need to have a 4.4 centimeter arrow perpendicular to the ramp. Okay, so that is 4.9 centimeters straight down. Okay, so that is my force of gravity. So my force of gravity, and then I need to have a 4.4 Newton arrow that is perpendicular to the ramp. So please make sure this is completely perpendicular. Mine doesn't look very perpendicular. And then we can add in the components. Now the components are just part of the force of gravity. Okay? And what I typically do for the components, this is the weight perpendicular and this is the weight parallel. I'll draw them as dotted lines just to reiterate the fact that these forces are not really there. They're really just parts of this greater force of gravity. And then the angle of the ramp is the angle between the perpendicular and the force of gravity. So this is the angle of the ramp, theta. Okay. And then if I want to figure out the acceleration, notice that this force and this force, these two are the same forces, same magnitude of forces. Okay. So it's really just the weight parallel that is actually accelerating my block. So if I do the acceleration being the F net divided by the mass, this is the weight parallel divided by the mass. That is 8.6 newtons divided by the 2 kilograms, which then, of course, that makes my acceleration 4.3 meters per second squared. Okay, for the next problem, we have 2 projectile motion problems. When we go through and solve projectile motion, what I strongly encourage you all to do is set up a chart that lists what you know in the horizontal, okay, or the x direction, and what you know in the vertical, or the y direction. Okay, so 2 things you know right off the bat is in the horizontal the acceleration is 0, and in the vertical the acceleration is 9.81 meters per second squared. Okay, down. And this will come more relevant down here. We're given the distance in the vertical, so we know the distance in the vertical, 45 meters. We also know the horizontal initial velocity of 30 meters per second. We also know that since it's moving horizontally, it is not moving vertically off the bat. Okay, so we say the initial velocity in that vertical direction is 0. So the first thing we want to do is find the time of flight. Okay, so that is our first unknown. So in order to find that time of flight, okay, I notice that I have a d, a vi, a, and t. So that is the fourth kinematic equation. That d equals vit plus 1/2 at squared. Now I'm dealing with this just in the vertical. So this is all vertical subscripts. Okay, and since the initial velocity in the vertical is 0, I want to find that time. So I'm going to multiply both sides by 2. I'm going to divide by my vertical acceleration. That's the acceleration due to gravity. It's an a. And then, of course, square root. So my time of flight becomes equal to the square root of 2 times the vertical distance divided by the vertical acceleration, which then that is 2 times 45 meters divided by 9.81 meters per second squared. And then the square root of that. So I worked this out to be just a little over 3 seconds. Now to determine the range, that is a horizontal distance. Okay, so our second unknown is that distance. So I could use the same equation, a couple ways of thinking about this, but one way to think about it is using the same equation, but now my acceleration in my horizontal is 0. Okay, and all that means is that it's not gaining or losing any speed in the horizontal. And if you ask yourself, well, why might this be? Because when it's in the air, the only force that's acting on it, it's in free fall. So the only force that's acting on it is the force of gravity, meaning that there's no horizontal forces acting on my object. So then I take my 30 meters per second, multiply it by my 3 seconds, and that, of course, is 90 meters. And that's my range. Okay, so for this next one down here, we have a projectile that's fired from the ground with an initial velocity of 250 meters per second at an angle of 60 degrees. So we have a scaling effect that we need to draw in, and once again, notice the theme with this review assignment. So we have 250 meters per second, okay, then 250 meters per second, and the scaling factor is 50 meters per second is 1 centimeter. Once again, I'm trying to do this so that I cancel out my meters per second. So this is going to be 5 centimeters. Now it's at 60 degrees above the horizontal. So what you're going to want to do is you're going to want to take your protractor and you're going to want to mark off, okay, a 60 degree angle from point P. Okay, so place the center of your protractor at point P and then make a mark at 60 degrees. And then what you're going to want to do is you're going to want to draw in a 5 centimeter line that is going in that direction. Okay, and then if you want to find the components of it, you have a couple of different choices. You could either find the components by just simply measuring these distances. Since you did it to scale, then you can measure these distances and then use this conversion factor of how many centimeters, 50 meters per second. Or you can figure out it by just simply using some trig, that the x component is v cosine theta and the y component is v sine theta. Okay, so your choice, but either way, you should get an x component of around 125 meters per second. It's going to be around if you're using the measurement method. And then likewise for this one, around 216, actually I guess 217 meters per second. So let's just call it 220 for those of you that are doing it to scale. Now to calculate the max height, okay, this is where we're going to actually need to do some calculations, or I guess projectile motion calculations. So I'm going to list what I know in both the horizontal and vertical again. Okay, I once again know the acceleration in the horizontal is 0 and the acceleration in the vertical is 9.81 meters per second squared. I know the initial velocity here is 125, and I know the initial velocity here is equal to a positive 217. Now here's where we have to be a little bit more careful. This acceleration, the acceleration due to gravity, if I drew a free body diagram of this object in the air, the force of gravity would be down. So the acceleration is down. So the way that we mark this off is we make the acceleration negative and the initial velocity will be positive. So if I want to figure out the max height, I also know that at the top, and I'm just going to write this v top, the velocity is 0. Okay? I know the final, right before it lands, is going to be the same amount, but opposite direction. That's going to become relevant later on. And then what else do I know? That's all. Okay, and I want to know the max height. So I want to know a distance when the velocity is 0. Okay, so notice that I don't have any time. Now I could actually figure out a time, but for this calculation, actually let's do that right now. Let's figure out the time it takes to get to the top. So I know a know a V at the top, so I'm going to call this my VF. I know a VI, and I know an A, and I'm looking for T to the top. So I could do VF equals VI plus AT. Okay. Now, since I'm finding the time to the top, okay, my VF here is 0. Okay, the velocity at the top. Then I subtract my VI, that equals AT, and then divide by A. So this becomes my negative of my initial velocity of 217 divided by a negative 9.81, and so I got a time of 22 seconds. Okay, so that's 22 seconds to the top. So to figure out that max height now, I can do D is equal to VIT plus 1/2 AT squared. So my initial velocity being 217 times my 22 plus 1/2 times my negative 9.81 meters per second squared times 22 seconds squared. Okay, and if you do this, you should get a max height of 2,400 meters to 2 sig figs. Okay, so now here's what's cool about this. The time it takes to get to the top is 22 seconds. So for this next part, the total time is going to be twice that, or 44 seconds. So if I want to figure out the range, that is my x component of my velocity, so it's initial velocity times time plus 1/2 AT squared in the horizontal, which, looking up above, the acceleration in the horizontal is 0, so this whole thing cancels out. So now I have my initial velocity in the horizontal, the 125 meters per second, times the total time in the air, right? It doesn't, if we kind of sketch this out, it's going to take a parabolic path down to the ground, and it's going to spend the full 44 seconds in the air moving horizontally. So that worked out to be, to 2 sig fig once again, 5,500 meters. All right, and then the last one in this assignment is a circular motion problem. It's a 4 kilogram model airplane traveling in a horizontal circle of radius 12 meters per second at a constant 6 meters per second. So the first two things is just simply drawing the velocity and acceleration vectors. So you know that the velocity is tangential to, well, that's not tangential, tangential to the circle. And so if I had to draw a tangent, okay, that is perpendicular to the radius, I would get a line that looks like that. So that's my velocity vector. And then my acceleration vector is inward. That's the centripetal piece. And I'm going to label that A sub c. If I want to find that centripetal acceleration, the centripetal acceleration is v squared over r. And so if we go back up, we have a velocity of 6 and a radius of 12. So that is 6 squared over 12. 6 squared is 36. 36 over 12 is 3. So we get 3 meters per second squared. And if we want to know the centripetal force, which is really, right, the net force for circular motion, that is equal to my mass times my centripetal acceleration. And the mass is given of 4 kilograms. So we have a mass of 4 kilograms times my 3 meters per second squared. and that is 12 newtons. Okay, so that's all for this video. I hope you enjoyed. If you have any questions, come see one of us, and thank you for watching. Have a great night. Bye-bye.